All right, well, we're calculating, in theory, these are the amounts we should get. In practice, we don't always get these amounts. And there are different reasons we might not get these amounts. Sometimes side reactions occur. For example, maybe a little bit of carbon monoxide or a little bit of soot might form. So we get a little less CO2 than predicted theoretically. It's a side reaction. Sometimes we try to collect it and we aren't very effective at collecting it. This would be like if you have a cookie dough. You know, let's say you have 1 pound of cookie dough. Are you going to use all 100% of that? It depends, you know. It depends on the container. Do you scrape? Yeah, probably. Maybe you might lick the container or something, get every last bit of it out. But sometimes it's hard to get all of it, right? And so sometimes it's just not worth it. You say, forget it. I'll leave a little bit, waste a little bit. And so that is something that we pay attention to, and measure how much of that we lose, how much of that we recover. And so what that's called is, let's see. Actual yield. So your book calls the ideal yield the amount of product formed from the complete converted. So the ideal yield is what I call the theoretical yield. More frequently it's called the theoretical yield. In Chem 1 it's called the theoretical yield, in Chem 7 it's called the theoretical yield. I don't use the ideal yield. So the theoretical yield is the yield based on stoichiometry. The actual yield is what you actually got. And typically it's lower than the ideal yield because you might have some impurities, incomplete reactions, side reactions, or you just might not want to scrape every last bit out of the container. Leave a little bit behind. And we compare the two. You know, ideally we want 100% yield. That is, what we actually got is what we should have gotten in theory. But in reality, we lose a little bit, and that little bit of loss will result in a percent yield that's lower than 100%. And so let's look at a problem involving this. All right, a solution containing 3.18 grams of barium chloride is added to a solution containing excess sodium sulfate. All right, so barium chloride, what's the formula for barium chloride? BaCl2. Is added to a solution containing excess sodium sulfate. Sodium sulfate's formula? NaSO4. Na2SO4. This is an excess. All right, what kind of reaction does this look like? Double replacement. What are the products? Products will be barium with sulfate, so barium sulfate, which is BaSO4, and sodium with chloride. The formula for sodium chloride is NaCl. All right, sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So barium is one of the exceptions. It will be an insoluble solid, which will form precipitate, which is the driving force of this reaction, precipitation. Since we have a driving force with this reaction, let's go ahead and balance this. One barium, 2 chlorines will need 2 sodium chlorides, and then it's balanced. So it's a 1-to-1, so we're going to have more than one. For every mole of barium chloride, we're going to have more than 1 mole of sodium sulfate. That's what it means to be in excess. Excess we abbreviate in chemistry as an X and an S. Excess. Calculate the ideal or the theoretical yield of barium sulfate. And so we're starting off with 3.18 grams of barium chloride. And so where do we go from here? Grams of barium chloride to grams of barium chloride to moles of barium chloride. So we'll go from grams of barium chloride to moles of barium chloride. From moles of barium chloride to moles of barium sulfate. And from moles of barium sulfate, we'll go to grams of barium sulfate. And so here's our stoichiometry map for this particular problem. There. And so we'll need some masses. What's the mass of barium? Just get it off this periodic table here. 137.33. 137.33. Chlorine is 35.45. We'll need sulfur. Sulfur is 3207. 3207. Oxygen is 1600. So that means barium chloride. 1 barium, 2 chlorides. So barium chloride's mass is going to be 70.9 plus 137.33. 208.23. And then barium sulfate. 1 barium, 1 sulfur, 4 oxygens. So 4 times 16 is 64. Plus 1 sulfur, 3207, plus 1 barium, 137.33. 233.40. All right, those are going to be in grams per mole. So we can go grams to moles or moles to grams here. So let's set up 3.18 grams of barium chloride, and then we'll convert it to moles. So mole barium chloride weighs 208.23 grams. So now we have moles of barium chloride, then we'll do a mole-to-mole conversion. It's a 1-to-1 mole ratio. 1 mole of barium sulfate for every 1 mole of barium chloride. And then we'll use the molar mass here, 233.40 grams of barium sulfate per mole of barium sulfate. So they're saying we have plenty of sulfate, we don't have to worry about that. And so this will be the theoretical yield, what we calculate here. So 3.18 divided by 208.23 times 233.4. 3.564 grams of barium sulfate. So in theory, we should get this much. But do you think you're going to scrape every last little crystal out of your test tube to weigh it? No. They're probably going to leave a little bit behind because it's just not worth it to spend hours trying to scrape every little bit. In fact, you see this person left some behind. They only recovered how much? 3.37. So this is our actual yield. The actual yield is 3.37. In theory, they should have gotten 3.56. But in actuality, they only got 3.37. And so what we do is we compare the two. Therefore, the percent yield is the actual yield, which we call AY, actual yield, over the theoretical yield. TY times 100%. And so the actual yield is the 3.37. And what they should have gotten is 3.56. 4 times 100%. Let's see what kind of yield they got here. 3.37 divided by 3.564. 94.55. It's like I should have 3 sig figs, so 94.6. 94.6%. So that means they recovered 94.6% of the product, and they lost 5.4% product. So this is a percent yield. Let's see what the book did. Pretty much the same. They rounded things a little differently than I did. They got a 94.7, I got a 94.6. So how do we use this? One, we could just see how much we lost, how good a recovery is. Maybe we need to improve it, or maybe it's good enough. Another is we could make predictions, based on it. And so, there are 2 ways we do this. One way is just this. So now I have that number. How can I use that number? Well, let's look at examples of using percent yield. All right, A. If we always get the same, let's say our technique is pretty consistent, then we can make some predictions based on, we can just anticipate. Let's say you're making cookies. You're baking cookies and you have a 90% yield on the cookies. You lose about 10% of that. And so if you plan on baking, let's say you want to bake 100 cookies. And so you set out, your recipe is for 100 cookies, but you're only going to end up with how many? Well, you're only going to end up with 90 actual over every 100 theoretical. And so if we set out to bake 100 cookies, we're only going to end up with 90 cookies. That's it. What happened to the other 10? Well, the other 10, you might have gotten hungry or something. Or whatever. Lots of reasons. Okay. Or B, let's say you have an event. You have an event. And this event requires 100 cookies. 100 cookies required. And so what we need is an actual yield of 100. So how many cookies should we plan on baking? If we need an actual yield of 100, then maybe we should bake how many? 110? If we make 110, then we could lose 10 of them. Is that right? It turns out, no, it's slightly off. We should bake 111. We should bake 111. Why? Because of this. If my actual yield needs to be 100, and so this is 100 cookies actual yield, then I know that for every 100 in theoretical yield, I only get 90 in actual yield. And so this takes me back to, in theory, how many should I make? Well, that's going to be 100 times 100 divided by 90. 100 100 times 100 divided by 90 is 111.1 cookies. So maybe I should make 112, just to make sure I have a full 100. And so this will be my theoretical. So I better prepare to make 111 and anticipate getting 100. Well, in chemistry, we do the same thing. If you already know about how much you're going to lose, then you need to prepare in advance for that loss in your calculation. So we do the same thing. We'll try it here in this particular problem. This is a big chemical problem. Solid sodium nitrate decomposes to solid sodium nitrite and oxygen gas upon heating. One set of reaction conditions gives a 95% yield. So they already know they're going to lose 5%. So if they already know they're going to lose 5%, what they want is what mass of sodium nitrite will be produced by decomposition of 1.5 grams of sodium nitrate. And so they can kind of predict how much product they're going to get in this particular reaction. So this would be an example of A here. Okay, so what is sodium nitrate's formula? NaNO2, NaNO3, nitrate, 3, NaNO3. This is solid, and then they're going to heat this up, heat it, and then it's going to decompose into solid sodium nitrite. What is the formula for sodium nitrite? NaNO2 and oxygen. What's the formula for oxygen? O2. Okay, this is solid, this is gas here. All right, next we need to balance this. How should I balance it? Two ways to balance. I got one sodium, one nitrogen, 3 oxygens, 2 plus, I got 4 oxygens here, but I could cut this in half. Get a half a mole. But do you like fractions? No. So I could double everything. But before I double everything, let's take a look at this reaction. What kind of reaction is this? Is this a metathesis reaction? No. Is this an acid-base reaction? No. This must be a redox reaction. If it's a redox reaction, what's the oxidizing agent and what's the reducing agent? Well, in redox, we have an oxidizer and we have a reducer. So what is the oxidizer, what is the reducer in this particular reaction? Well, going forward, what's the OA, what's the RA?
Sodium's reducing.
Actually, sodium, let's take a look what happens to sodium. What's the oxidation state of sodium? Sodium is group 1. Group 1s have an oxidation state of +1. The oxidation state of sodium is +1. What's the oxidation state of sodium here? +1. Did sodium gain or lose any electrons? No. So nothing happened to sodium. Sodium is a spectator. Let's take a look at nitrogen. What's nitrogen? Well, nitrogen varies. And so it's probably best to go with oxygen next. What's the oxidation state of oxygen? -2. If oxygen is -2, then nitrogen is +5. let's go over here. What is the oxidation state of oxygen here? It's -2. What is the oxidation state of nitrogen? +3. So what happened to nitrogen? Nitrogen went from +5 to +3. In order to go from +5 to +3, did it gain electrons or did it lose electrons? +5 to +3. It lost. So for example, if sodium goes from plus to 0, did it gain electrons or lose electrons? It's going to gain. So a positive and a negative charge will make 0. If sodium ion loses an electron, we have to form sodium 2+ plus an electron. 2 positive charges and 1 negative charge will leave it +1 here. See that? And so how many electrons did nitrogen gain? 2. Each electron is going to cancel out 1 positive charge. We cancel out 2 positive charges, so we got 2 electrons. But who? So I know that nitrogen took the electrons here, but who did the nitrogen take the electrons from? It's got to take it from the reducer, but do you see a reducer there? So I know my sodium nitrate is my oxidizer. What's my reducer? Now this is the weird thing here for this particular type of reaction. I have 3 oxygens. Here I have how many? 2. So 2 of the oxygens nothing happened to. 2 of the oxygens went from -2 to -2. Nothing happened. But 1 of the oxygens went from -2 to 0. And so this is a very weird reaction. This is a very weird reaction because sodium nitrate is both the oxidizer and the reducer. The nitrogen in nitrate is the oxidizer. The oxygen in nitrate is the reducer. That is weird. That's weird. That doesn't normally happen. That doesn't normally happen because nitrate, you know, we normally think of as an oxidizer. But when you heat things up, things become more violent, more chaotic. And so as these atoms are vibrating more chaotically, more violently, what can happen is the nitrogen can attack itself. I mean, the nitrate attacks itself, basically. In other words, the nitrogen, oxygen doesn't want to give up those electrons, so it's very difficult for it to take the electrons. But if it's hot enough, then the nitrogen will actually attack one of its oxygens and take its electrons. See, to form that. Why is that? Well, one of the reasons is because nitrogen in a +5 state is electron poor, electron rich, or okay as is? Electron poor. In fact, the charge on nitrogen varies from what to what? I'm sorry, what is it? Not -5. -3. -3 to +5. So this is the most electrons it can lose. It's already lost 5 electrons. 5 electrons. Wow, it's very unhappy. And so this makes it very desperate for electrons. Normally at room temperature, it's not going to attack itself. You know, the nitrate's not going to attack itself. It's got to be very hot to do that. When it gets very hot, then something might happen like that. Rather, much more preferable is nitrate attacks something like a reducing agent. And so there are other reactions of auto or self-reaction. So this is auto or self-reaction. This is not a very favorable one because oxygen is very happy with -2. This is a much more favorable auto reaction. Let's take a look at this one. Ammonium nitrate. If we look at ammonium nitrate, then we know that nitrate is electron poor, electron rich. We say nitrate is electron Well, nitrogen nitrate is +5. So nitrogen and nitrate is +5, meaning it's, and oxygen is -2. Well, oxygen is happy at -2. It's not really rich. And so this is electron poor. Nitrate's electron poor. How about ammonium? You know, if I look at the ammonium ion, is that electron poor or electron rich? What's the charge on hydrogen in ammonium? What's the charge on nitrogen? The oxidation state? -3. So in ammonium nitrate, one of the nitrogens is -3. It's gained 3 electrons. The other nitrogen, there's 2 nitrogens. The other nitrogen is +5. It's lost 5 electrons. So there's a difference of 8 electrons. This nitrogen versus this nitrogen has 8 more electrons than this nitrogen. Is that an equitable situation? You got 2 nitrogens. One nitrogen is going to hog up 8 electrons. The other is going to have 0 electrons. Is that, what do you think? Is that a stable situation? No, it's not a stable situation. And so what you have is you have an electron-rich species, ammonium, and an electron-poor species. This one you don't need as much heat. This one you're going to need a lot of heat. This one you don't need as much heat to get going. But you know, there's a lot of potential energy. This one doesn't have as much potential energy. This one has a lot more potential energy because that's a great reducer. However, oxygen with -2 is not a great reducer. And so ammonium nitrate has led to 2 of the biggest industrial disasters. So I should show you those here. I'll show you the more recent one. The most recent large industrial disaster happened in China. You might have seen this already. Is this it?
The tank over here is filled with carbon dioxide gas. Now carbon dioxide is...
That's not the one I wanted to do, sorry. I guess this is it. Let me try this one. This is for the language. There was some language there. I just wanted the original footage, not the edited one, which was this one here. I don't know.
Holy shit!
If that's okay, the uncensored version, or do you want the censored version?
Fuck yeah, I'm videoing. What the fuck?
I think that might be a gas station or something.
Fuck yeah, it's a guess. Whoa! Oh! What the? Holy shit! No fucking what? Oh shit! Oh shit! No, baby! No!
Are we dangerous here?
Yeah, we're dangerous! Oh my god! Oh dear!
Are you filming?
Yes, I'm filming!
Wow! I think we are dangerous.
Let's go! Let's go!
Yeah, that's pretty crazy, isn't it? But that was in China. The worst industrial accident in the U.S. happened in Texas City.
This is Charles Hadlock. Texas City has tried to outlive its past, but it's hard. There are so many reminders. An anchor here.
Oops. That's the wrong one.
You can't spend much time in Texas City with all the big ships that come and go, the oil and chemical refineries, the pipelines and storage tanks brimming with flammable products. You can't spend much time here without thinking the unthinkable. Could it happen again? Could Texas City be another boom town in the worst possible way? 50 years ago, Texas City burned its way into the nation's conscience. The worst industrial accident in American history made Texas City synonymous with disaster. The day it happened, Will Lane was very near the epicenter.
Real frank, I'm real glad to be alive.
Lane was a young chemist at the Monsanto chemical plant. He remembers seeing the bright orange smoke from a burning ship. Firefighters were busy pouring water on the French freighter Grand Camp at the city docks across from the Monsanto plant.
You could look at it, it was real pretty to watch. And there were townspeople about 100 that lined the part of our parking lot that was nearest to the ship. They came down to watch a fire.
Texas City had a new fire truck, and this was its first day out. 27 firemen were on the docks trying to put out the fire. The burning ship was so hot, the water around it was boiling. But as a chemist, there was something about that orange-colored smoke that worried Will Lane.
We could just see bits and pieces of paper bagging going up to the air and away. And my boss thought, and I thought too, that we were witnessing a nitrate fire. But someone had said, it's a grain ship. The grain is on fire.
So believing it was only a matter of time before the fire was out, Will Lane went back to work at the Monsanto lab. But the fire was growing hotter, and the orange smoke was attracting an even larger crowd along the docks.
And it was a very, very strong sulfur in the air, sulfur fumes.
Herb Metzger watched the fire while talking to a group of high school kids.
This smoke was just a beautiful orange.
Mary Hunter, the Monsanto secretary, was watching from her office window. And across town, Mrs. Knappenberger, a housewife with a home camera, came here to the Texas City dike to get a closer look at the burning ship. She didn't know it then, but she was about to record America's greatest man-made disaster. The ship had been loaded not with grain, but with ammonium nitrate fertilizer, the same ingredient that would be used years later in the Oklahoma City bombing. The Texas City blast was so strong it registered as an earthquake in Denver, 900 miles away. It created a tidal wave that washed a barge into a parking lot. 2 airplanes circling the ship were blasted from the sky. Flying debris punctured chemical storage tanks, creating an even larger inferno.
We have another truck up here off of the road. It had about 10 or 15 men, and they were all crushed.
The explosion killed at least 581 people, including school children who had come to watch the fire. But the danger was far from over. Tomorrow, we'll hear the stories of survival and courage from the people who were there 50 years ago. Charles Hadlock, 11 News, Texas City. This is Charles Hadlock. Texas City has tried to outlive its past, but it's hard. There are so many reminders. An anchor here, a propeller there, and sad, sometimes painful memories all around. Even today, 50 years later, the tragedy is not forgotten. 6th Street, the once busy main street of Texas City, has been renamed the Street of Memories. For it was along this street that so many screamed and ran for their lives. The explosion of the French freighter Grand Camp left an entire town dazed and confused.
And I ran as fast as hard as I could.
There are many stories of survival. Dr. Will Lane was in the Monsanto lab. He had been watching with suspicion the bright orange smoke of the burning ship docked next to the plant when it suddenly exploded.
And when the lights just went out, I could not see more than 2 or 3 feet. And I thought, my God, it was a nitrate explosion. I'll probably lie right here and be burned to death.
He got up, looked over his shoulder at the burning tanks of benzene, and ran for his life.
Passed a car in which 2 people had been decapitated. Then I passed on the 2 little planes that had been flying around overhead. Came down along the path that I took up to the town.
I'm sure all of that glass came into us, and I must have gone like this. And so my arm was injured all in here.
Mary Hunter was also in the Monsanto plant. To this day, she still has shards of glass in her body.
I had it cut out of me, but luckily it had lead in it. And therefore when they x-rayed it, they could find the glass.
Before the explosion, hundreds of people were on the docks, including Herb Metzger.
I had turned to walk away. I had my back to the explosion, but the force hit me in the back, and it sort of just, I don't know, I would say it picked me up, but it blew me forward 20 or 30 feet.
Suddenly, pieces of the ship were falling all around him. He crawled under a car.
A couple of pieces hit the car. I could feel it, you know, when it jarred, but nothing hit me.
Here comes another explosion. But pieces of metal did hit the High Flyer, a second ship loaded with ammonium nitrate. Efforts to tow the burning ship out to sea failed, and 14 hours later, it exploded. The fires burned for days. Nearly 600 people died, and 5,000 were left injured or homeless. Those who survived helped each other.
Well, we had to pry some folks out that had telephone poles, in fact, I guess, or some kind of big poles blown across them. They obviously were crushed, you know. It was not a nice sight, but kind of steeled myself to it for a while.
Even after the dead were buried, many survivors never talked about it again. But over the half-century since the explosion, they rebuilt their lives and their city. That must have been a hard thing to do, with so many memories around. Charles Hadlock, 11 News, Texas City.
Okay, so something like sodium nitrate is going to be a lot harder to decompose than something like ammonium nitrate. And ammonium nitrate is also going to decompose, and so the oxidizing agent and reducing agent are the same compound. Just like in this decomposition, the oxidizing agent and the reducing agent is the same compound, except the reducing agent isn't nearly as good as that one over there. So, see that huge difference. But what mass of sodium nitrite will be produced by decomposition of 1.5 grams of sodium nitrate, assuming there's a 95% yield? So let's go ahead and do this here. So first we need the balanced chemical equation. And then what we're going to do is this. We're going to go with 1.5 grams of sodium nitrate. So 1.5 grams of sodium nitrate. And then we're going to go from grams of sodium nitrate to moles of sodium nitrate. And then from moles of sodium nitrate to moles of sodium nitrite. And then from moles of sodium nitrate to grams of sodium nitrite. But this grams of sodium nitrite is the actual yield or the theoretical yield? Stoichiometry is going to calculate the theoretical yield. So this is my theoretical yield. And then what I'll have to do is I'll have to do one more step to get my grams of sodium nitrite actual yield. There I'm going to need the percent yield in order to do that. So let's go ahead and set this up. But first I need to calculate some masses. So sodium is 22.99. Nitrogen is 14.01. Oxygen is 16.00. And so sodium nitrate, we have 3 oxygens, is going to be 48. Plus 1 nitrogen is 1401. Plus 1 sodium, which is 2299. And so sodium nitrate will be 85.00 grams per mole. And then sodium nitrite just has 1 less oxygen. So let's take that minus 16, 1 oxygen. That gives us sodium nitrite is, 69.00 grams per mole. Okay, so let's go ahead and do that. And then we have a 95% yield. The 95% yield, we need to make that into a conversion factor. So 95% yield means that we're going to have 95 grams of actual yield for every 100 grams of theoretical yield. And so this is the actual yield of sodium nitrite over theoretical yield of sodium nitrite. And so we're going to use that somewhere here in the final step. Okay. So let's take a look what we have here. Okay, so setting this up, we'll start off with 1.5 grams of sodium nitrate, then convert that to moles. 1 mole of sodium nitrate weighs 85.00 grams. So now we're here at moles, and we're going to do a mole-to-mole conversion. Turns out it's a 1-to-1 mole ratio. So 1 mole of sodium nitrite for every 1 mole of sodium nitrate. And then we're going to go from moles of sodium nitrite to grams of sodium nitrite. And that's 69.00 grams of sodium nitrite per mole of sodium nitrite. And then finally, in stoichiometry, this would be called the theoretical yield. And so what we need to do is we need to go from theoretical yield to actual yield. And so I'm going to go 95 grams of sodium nitrite, or actual yield, let's see, actual yield of sodium nitrite over 100 grams of theoretical yield. Okay, and so this will give me my actual yield here. And so let's calculate this. It's going to be 1.5 divided by 85 times 69. And so my theoretical yield is actually 1.217 grams. But I'm not going to get all of that. I'm going to lose about 5%. And so I'll do times 95 divided by 100. And my actual yield is going to be a little less. It's 1.156 grams. So I'm going to lose a little bit. And so I'm allowed 2 sig figs. So it's going to be 1.15 grams of sodium nitrite. Actual yield for 1.2 grams of sodium nitrite. Actual yield. Okay, finally we're going to look at energetics of reactions. We'll talk about energy. You know, this particular reaction is called endothermic because we need some heat here. Ammonium nitrate decomposition is kind of weird, you know, because initially you need heat, but then it releases a huge amount of energy. Like, you know, what happens with flames like this or explosions is a lot of energy is released in a short period of time, and so if you can release that energy over a long period of time, then it's not so violent. But if you release that energy over a short period of time, it becomes quite violent. So that's what happens with some of these. Like, so, for example, and then there are other things about energetics. Like, if you do a precipitation, you know, let's say you're going to precipitate out silver chloride, do you necessarily worry about an explosion occurring when you generate this white cloudy PPT? No. When you do precipitation, you aren't going to have an explosion like that. How about effervescence? Like when you generate a gas, like bubbling gas. Well, that could get violent potentially, but you don't really worry too much. You know, there could be a pressure explosion, effervescence. There can be some heat generated. The same thing within acids. So metathesis reactions, we really don't necessarily worry too much about explosions. Acid base, you could take a strong acid and react it with a strong base, and you might not get an explosion there either. You know, the worst explosion you'll get when a strong acid reacts with a strong base is a steam explosion. You know, where a lot of steam is generated because so much heat. But you don't have a violent flame or a violent explosion there. It's only in redox reactions. And the reason for that is this. In metathesis reactions and in acid-base reactions, the oxidation states don't change. And so in metathesis reactions, you start off with calcium 2+, you end up with calcium 2+. But in redox reactions, the oxidation state changes. And then there, things, you know, the elements behave quite a bit differently. And so a simple example of that would be sodium ion. You know, sodium ion, that's pretty stable. It's unreactive, sodium ion. You know, what metathesis properties does sodium ion have? Pretty much zero, very little. What acid-base properties does sodium ion have? Pretty much nothing, it's neutral. What redox properties does sodium ion have? Pretty much nothing, because sodium ion is not an oxidizer, but it's one of the weakest oxidizers on the chart. So sodium ions are pretty stable. They're pretty unreactive. But if we contrast that with sodium metal, now that's a huge difference. Metathesis, sodium metal, nothing. Acid-base, sodium metal, nothing. But redox, sodium metal, something. What is it? Sodium metal is a very powerful reducing agent. And I showed you what happened when they dumped the sodium metal. Do you remember the drums of sodium metal being dumped into Lake Lenoir, Washington? Yeah. And so that's the difference. And so there's a huge difference in reactivity between sodium ion and sodium metal. Well, that means there's a huge difference in energy, in potential energy. Sodium metal, high potential energy. Sodium ion, very low potential energy. And all that energy, this is called the first law of thermodynamics, all that energy has to go somewhere. And the first law of thermodynamics, does anybody remember the first law of thermodynamics from chapter 1? Yeah, exactly. Energy cannot be created nor destroyed. So if there's a huge difference in potential energy, then that's got to go somewhere. Where does it go? It goes out into the environment. And we get explosions and stuff like that. And so this is why for redox reactions, they can be potentially extremely violent compared to acid-base reactions and metathesis reactions, which aren't. So I'm going to stop here. See you next time.